on Monday, we saw the 10 commands that allow you to create files, create folders, move across the tree, the different branches of folders and files on a Unix or Linux system. Now, if you want to create files, well, most of those files, or at least the files that you most likely will interact with, will be text files. You will be writing usually small files where you will prepare the submission of a job, or you will be reading and copying on do something with the output or the input files. Is very common in this for scientific codes that you have to write an input file. An input file is a text file usually that contains the different instructions or the different setup for a code that will compute the simulation, for example, in physics, okay, a set of variables that declare positions of atoms or physical conditions, or in the case of engineering, some geometry, but that geometry eventually could be something on a different format, but at least there is like a text file that will tell the code, okay, this is what I would like to simulate under these conditions. So it's important for you to know how to edit files, to edit text files. So we will be focusing on what we call terminal-based text editors. Of course, on a cluster like this, you don't have access to blah, blah. You can, but in most cases, you will not be using a graphic text editor, and then this is completely different from using like a word processor, like Word or those things, where the content is also attached to some formatting. So that is for writing letters, that is for writing documents of that nature. But here we are talking about plain text, so just the text, just the characters, and the formatting plays a very minor role here. And those editors will run directly from the terminal, directly on the terminal. And we will see that with exploring a little bit one example here. And I usually show 3 text editors. Now that we are compressing the workshop in 8 hours, I will just mention the 3, but I will just focus on one. Is good for beginners, so that is what I will be focusing, because I'm not expecting at the beginning that you have to edit complex files and do extravagant and copying and paste, things that are more advanced. So that is the editor that will be used. After that, it's a matter of choice, a preference. Some people like to use Emacs, which is another text editor that is very powerful. It allows you to do very, very complex text manipulations of text, and Vim or VI, which is also an old, well-established, powerful text editor that is often used by system administrators, especially because it's something that you rely its existence on basically all Unix machines. So if you learn VI, you have some assurance that it should be there. It should be on any machine that you put your hands on. Unix machine that you put your hands. So you end up choosing one of those three in the long term. People usually start with none, and later on, when they get more speed or their usage of the cluster become more prevalent, they usually jump into one of the other two editors, and they will continue developing. They will continue working with that. So a few notes here that you can read here. Some of these editors have been around for at least 30 years or even 40 years. So they are old. And back in the 80s, 90s, well, some of the keyboards, they have slightly different keys that over time were replaced, for example, on a Mac with the command option control. They are very typical with the weird symbols that they have on top, like a tiny flower. In the case of Windows machines, well, you see the Windows icon on the left of the space bar. So those keys that used to be different, or you used to have a different name back in the 80s, when the way you work with a computer, it's a little bit similar like we use today with a terminal, but what you have were dumb terminals. So all just a monitor, just a keyboard, and a text interface, no graphics, and you connect. And those terminals, well, they were called VT100, or they're all terminals. And with those machines, you connect relatively remotely to a mainframe. So some machine that was on the same building somewhere. And that's how people at that time interact with the machines. I'm talking about the 80s and beginning of the 90s, before the popularity of personal computing. So we have mainframes, and we have machines where you connect to those. And at that time, from that time I'm talking about, is the presence of those, for example, the meta key that over time was replaced with the Windows key in Windows machines, or on Macs is the option and command keys. So when I mention those keys, or when you see those keys on some text editors that you have typed, they are usually referring to that. They call it meta, but it's actually the Win key or the command button on the Mac. Okay, so the first editor that we will review is Nano. It's very simple to use. I will make a small demonstration how you use it. And for each editor, you will see that in the reference that you can find for the three editors that I'm showing here. I am focusing on basically 3-4 skills, minimal skills, that allow you to do effective work with a text editor. Those skills are opening and closing a file, which is something that in some of those editors is not so trivial. So you could easily get stuck and you open the file, and after you don't know what to do, how do you leave the text editor. So that's something that you need to learn. And this is a good thing that you learn, at least for all of them, in case that you don't feel comfortable at some point and you want to leave the editing of a file with another editor. But in the case of Nano, it's very simple because they have a bar. You will see in a minute how that works. So one of the skills that is important is opening and closing a file, or entering and leaving the text editor. Another thing is to move around on the text, moving across the text, jumping from one location to another. Usually you can at least use the arrow keys to move backward and forward, to the left, to the right. and not necessarily, but the VI in the original version, you have to use different keys, even for movement, because at that time they don't have arrow keys on keyboards, so people have to use some of the letters to actually move across. Copying and paste, this is something that you do very often with a text editor. Some lines, when you are writing that, they're very similar. So what you do is you copy a section of some of those lines, you paste that, and you start introducing small changes, and search for a specific text and replacing some text for another. Those are the very minimum that you need to learn from a text editor to do something. I am focusing on small files. If you want to work with big files, let's say the typical files that you get at the end of a simulation, for example, in physics, in chemistry, in bioinformatics, what you get is a huge text file that could have millions of lines. So it's not practical at that moment to start moving across that file with arrow keys, and you will not read the file entirely. What you will doing is basically searching or doing jumps, let's say 1,000 lines, 10,000 lines, and moving that way. So it's important for you to learn those things. Okay, so that's it. I will do the demonstration in a minute. The other editor, at least you should know how to enter and leave the editor, is with this sequence of commands where you write it here or there, here. I will show this in a minute. This editor is powerful, but it relies a lot on multiple keys that you have to press simultaneously to get some effect. That is the characteristic, and for some people the advantage, for some other people a handicap of the way this editor works. So the fact that you have to press multiple keys. And here you see the sort of combinations, key combinations, usually is with control. You see here where they say C, uppercase C, it means that you have to hit the control and another key, and after that another control, another key to do some effect on the file. When they put the letter M, is the meta key that I just mentioned that you have to change for either the command key or the Windows key. It depends. So that's Emacs. This is one of the candidates for power users, let's say, and VI or Vim. This is another special editor. Compared with Emacs, this is a mode editor. You have to change between modes, and when you are in a certain mode, you can execute commands without relying on too many keystrokes, multiple keystrokes, or simultaneous combinations of keys. But when you just start, you have to enter into the insert mode just for typing a minimal amount of text, and you have to leave from the insert mode into a command mode or normal mode to execute something like searching for the text or something. I will probably demonstrate a little bit, but my focus will be on Nano because that's a very minimum, and for the exercise that we'll be doing today, Nano is enough. Nano is all that you need. So you see here a nice card with all the different keystrokes or the combinations that allow you to move blocks or lines up, down in the, opening, searching with this editor. Usually, if you select this one, it's a very powerful editor. And the advantage is you can rely that this exists, probably no Vim, but at very least VI exists on any Unix environment. It's like an standard. So let's start with this, and I will be trying to demonstrate this. Let's see if I can do it. changing the way I'm sharing my screen. Okay, by the way, before I change the screen, if you want the materials, some of the materials, I need to update a little bit this. But here on the setup, this is at the very end. This is the line that you have to execute to get all the examples for this version for introduction to HPC. I will show you this in a minute, but this is the command is here. You just execute this command and you will download all the materials. So let's go back here. So what I'll be using is the text editor for our first exercise. Now I will be changing. I will be cleaning this. So this is the first thing. If you want, here is the line that you need to execute. I will remove this. So this is the line. With this line, we will download in all the materials, the exercises that we will use. It's not that big, it's a few 100 megabytes. And when you go inside this folder, there is another folder called Introduction HPC. And here are the materials. So let's start with the number 4. So it's number 4. So our first exercise is, well, write text like what you see in exercise number 1 on the documentation on our material. And so I will be opening with Nano, for example. I will continue editing with Emacs, and I will finish in editing the file with VI, just to give you an idea the different options. And I will be using a slightly different name for the file. So let's start. First lines, I will be using Nano, after Emacs, and finally with VI. So this is what you get when you start using Nano. You get on top of the screen, it will take your entire terminal, and on top you will see the name of the file, so you know which file are you operating, and on the bottom you see 2 lines there that tell you of common combinations of commands that you use to move, copy, and do something with the text. So if you want to, let's start with the first line. You can just start typing. By the way, the commands below, when you see the hot, this is the control key. This is another way of saying the control key in computing. So I will start writing. This is a code that we will be able to compile in a minute. This is C code. We will not be entering the details of this, but I will be writing this. I will be writing this define here. Okay. Let's keep it like this. So in the case, by the way, if you will later want to compile this, be sure that works. you need to be careful. It needs to be exactly as I'm writing this. In C, the case matters. So it has to be exactly the same casing. Spaces are not so relevant, but basically all the text must be as it is on exercise 1. Okay, so I wrote a couple of lines with Nano. You see, I can use the arrow keys to move forward, backward. This is convenient. The first thing that I will be doing is exiting from this file. So you press the Control and the X key to leave from this edit. It will say, okay, do you want to save the changes? Yes, no. Okay, you will say yes. Do you want to save that with the file crp.c? And you just hit enter to confirm that the name, otherwise you just delete and change the name. So that's and you hit enter and you just wrote the first line of that. Now I will be using another editor for the next few lines of this. So the other editors is Emacs. On this editor, again, you can use the arrow keys to move forward and backward. And you can just type directly, and there is no problem with that. Another advantage, for example, of these kind of editors, like Emacs or VI, is that they include a code highlighting, or they understand several text formats. So if you are writing a file that has the name .c or cxx, certain extensions, it identifies that file as being a C file, and the editor knows which are the special words, which are the special characters, and it will be putting colors to the file, which is very convenient for developers, by the way. So if you are developing, you probably will prefer at some point to use a text editor that give you this advantage. Let's type a little bit. Spaces, the tabulators here are just optional in the C language, different, for example, from Python, where they are extremely important. But in C, they are optional. They are just, it's good to have them for organization of the code. And let's see. Okay, so I just wrote this. And now, let's keep it like this. I will be finishing the rest of the code with the third editor, but I would like to keep it like this. So I wrote the first lines with Nano, now these lines with Emacs, and I will finish with VI. So to leave this file, to save and leave the file, you have to press the Control key, the X key, keeping the control down, the S key, and with that, you have saved the file in the drive, in the storage. So that is to save the code, the drive, to save the content of the changes into the file effectively. By the way, these editors, for most part, they will not save with the changes that you do, except when you ask or you explicitly save the content. If you just leave or something happens with your internet connection, you could be you'll be losing whatever you edit from the last save. It's important to save often. And to leave from this editor, you press the Control key, the X key, and the C key. So I will show you the. So this probably is here. This is something that you need to know, because otherwise it's like this. This is to save the file, and this is to leave from the editor. Otherwise, you will get stuck in the editor. And so this is important. Even if you will not use it at some point, you prefer to use something else, you should know how to leave the file from the editor. And finally, I will be typing the end of the code with bin. So this is like this. You see, if you start typing, it will be not do anything. For example, I'm typing the key F, will not do anything. On the contrary, if I start typing, for example, something else, the letter D, and I start deleting lines from this. So in this case, I am not in insert mode, in command mode. So the keys on the keyboard, they are executing commands. They are not entering text. In this editor, if you want really to insert text, you need to go into insert mode. And to go into insert mode, you press the letter I. You see on the bottom of the terminal the word insert. If you want to leave from the insert mode, you press the escape key. Escape key, well, regardless, you press that, you leave, and you return to command mode, and you press I, and you go back to insert mode. So now you can start putting some text. Let's start with the loop. Okay. So now I will be I will edit these files, and as I told you, I will be focusing more on Nano, even if it's not the editor that I use. So I will be a little bit slow with this, with Nano, but that's for beginners is the best editor to start with. So let's keep it like this. I hope I typed this correctly. I think so. So I will edit the final lines here. I will probably like this. So the rest of the text I will be using that. So to leave this, to save or abandon this text editor, well, there are several things. First, you need to leave from the insert mode. So you press escape. And there are a few things that you can do. One is to put just column and W to save, as we did before for Emacs. This, you save the file into the hard drive and then to the storage device. And to leave from this editor, well, there are several ways. One is to press this, which is also saving. So it's saving and leaving. Or if the file you don't want to save, or you want to leave, you just press escape. You ensure that you are not in insert mode, and you press colon and Q and this to enforce it, and with this you leave. So 3 editors, all of them work. They are often used in most HPC clusters around the world. So most likely you will have at least two of those available for you on a cluster. So we have the 3. Different people will use whatever they want. So let's finish in this, because I would like to do a few things with this. So let's explore a little bit what you can do with that. So I told you, moving to with the arrow keys. If you want to go to the first line, it's not working. Let's focus on the copy and paste. Okay, let me type this. So if you see these two lines that are in exercise 1 are very similar. So what I will be doing is to copy one and just enter the changes, just to demonstrate what you have to do. And so this is a for loop, and for this loop, I will be doing this char and one space. And what I would like to do, instead of typing, which is something that happens usually in code, that you have blocks that are very similar, and you can just copy the block and do a few changes. I will be doing this here. So you can see, because I'm not used to this editor, so I need always to see. Okay. So in my case, another way of replacing the meta key on my Mac, and I'm using a newer Mac, so this is like you press the escape key and the letter A to start marking, and with that you can select the amount of text, the text that you would like to copy or. So I will be doing something that often I use, is to cut. So I'm removing the text, but I'm keeping a copy of that in memory. And after to paste that is with you. So this is what I would like to do. So I cut and I paste. Usually because I remember the cut easier on this. And now I can continue editing the file. So let me go back and recover the text file that I need to edit. So here. So what I need to do here is to replace this here for 0. And here it's x plus y less than size. And the increment is x plus plus. And I will be doing here is, well, not this. But print f x and this one. Okay, it needs to be very, very exactly. You see how the number of spaces, 1, 2 to the space, because this will print something on the screen. So I need exactly 2 spaces here, and it's just 1 space here, and here is a start and 1 space. So it need to be exactly like this, and any line in C code, in C language, instruction line needs to end with it. semicolon. I am facing. If I type this correctly, and I hope I did. Yeah, I think I did. Now we can compile it and execute it. So let's do that just for the exercise. But the idea is use your text editor. You see here on this on the content of this session on this episode how you can edit a text file. If this is the first time that you are using something like this and you are used to a Windows machine where everything is at least the notepad around, and you are not familiar with this way of working, start using Nano first. Over time, during the term of your PhD studies or master, whatever, you probably jump. But that change will happen naturally as your learning progresses and your needs changes or become more demanding. So now I will be leaving this file. So Control X. By the way, now that I know, I would say yes. Now that I know where my meta key is, so it's escape and this to go to the bottom of the file, and escape and this to go to the top of the file. So if you see here on my Mac, which is, you see, not for names, for Nano, you use the backslash and the slash to move to the bottom and the top of the file. Why this is important? Because when you will start working with output files, the simulation will return a file with 3-4 megabytes of plain text. So that means hundreds of thousands of lines. So sometimes what you want is just to look at the very bottom of the file. And so it would be impossible to use, or it would be painful to use just the normal arrow keys to go to the bottom of the file. And often the home and end keys will not work. Those keys that you have, or you simply don't have them. And let's say you are using a laptop, those keys sometimes are not there. On a Mac, they are not at all. And so you have to rely on this kind of shortcuts to go to the bottom of the file or go to the top of the file, backslash and slash. So that is another thing that I would like to show. And just for entertainment purposes, I will be compiling this file to show you what it produces. This is a fractal, and what you saw there, and this is called the Sierpinski triangle. And what this code does is reproduce the triangle. Well, the actual fractal are infinite triangles inside each smaller triangle. So you have a triangle here, and they are dividing that in 4 triangles. And for the 3 triangles, except for the center, is a copy of the same procedure. So it's going up to the infinite with this. So this is a popular fractal, and the code is basically creating an approximation of that with the stars, with small symbols. So that is the first exercise that you see here. Let me see if this makes sense. Well, we can skip this. And just for also maybe on entertainment purposes, I will be using them to show you that today is often the case that you have the arrow keys and you can move with those keys up, down, left, right, no problem with that. But in the old times, before those keys were present, the arrow keys, what you have to use were letters for moving. across the file. So if you see in, let's say like a pink box in the content after exercise 3. So I am skipping the first the exercise because now we are compressing the time, and so you can see the materials are there. Let me see. Yeah, exactly. That. Back in the time with the temperature were low, yeah, we have snow. Yeah, so we use these keys. So you see, I'm pressing the J, the K for moving up, and H for moving to the. So basically, you press all those letters, and I think L. So with L, you move to the left. That is the only key that makes sense. The other are just because they are next to each other. So with H, you move to the right, to the left, and with J and K, you move to the bottom on top. Why this is important? Because if you end up using a system that is very lightweight, so they install it with a very minimum of stuff, or you are, I don't know, you are using like a tiny microcomputer or something that they're stripped with all fancy code or packages, you have just the plain VI. And the plain VI will not recognize the arrow keys, and all that you can do is to move around with these 4 keys that you see there. So that is so we are pretty much on time, and we can move to the next. Otherwise, there are a few exercises here. The idea here on exercise 3 was, let me see if I can. Here, I think it's here. Oh, well, no, you have to download the code. Let me see if that still works. Oh, I need to, oh, well, let me see. It used to have, okay, apparently it's not working anymore. Oh, no, check it. Oh, I'm curious. Oh, okay. So I will be editing the file. What I will be doing here is to paste this. This is something I need to correct. And when you execute this, okay, now it will download what used to be important at that time for the previous workshop, while the COVID data, all the deaths and all that was at that time, and I put that that table. And the importance of that table is that table is big, really big. So so it's really big. So if you want to go to the very top of the file, well, you use backslash. If you want to go to the bottom of the file, it will be the slash, escape slash or meta slash, and you go. And the file is really big. I would like to know. This is another command that is not in the 10 commands that I mentioned before. It's a command that I will be using on the final day of the final session, final hour with scripting. This is to know how many lines you have on a text file. So WC is a word counter. It will tell you the number of lines, the number of words. So pieces of text separated by the spaces, or tabulator, something that looks like a space, and the number of characters on this file. So you see we have 300,000 lines in this, which is normal in when you start processing data or doing simulations, you get files like this, and you need to navigate on that file. So this exercise is trying to invite you to explore that sort of thing. But let's move on to something that is more important. I probably will devote slightly less amount of time to the environment modules, but it's important for you to know what this is. Imagine your computer. Your computer, well, you using Windows, but it's your computer. So you know what you need. And you go and buy or download or somehow install the software that makes sense to you. It depends on what you do for a living, what is your research area. Well, you will be installing that pieces of software that are relevant for you. In our case, our HPC cluster is serving hundreds of people. So we have more than 200-300 users, I think, and all in all areas of science, from basic science to social science to health science, all of that. Of course, in this variety of users, there is also equal variety of needs and software that they want to use on a cluster like this. So what we do is to have a way, like a software switch, that allow you to enable and disable software at will. Not only that, some people often needs different versions of the same subpackage, of the same software. Usually on your computer, if you get a newer version of the text processor, well, you just uninstall the previous one and install the new version. But sometimes you need to check, or something that was working on a previous version is no longer working on a newer version because the input file changed, or because the way the algorithm that used to work before is no longer working, and you need to check or reproduce something from a paper that was from 2 years ago or something. So you need different versions. So this is another reason for having a system, software package that allow you to switch on and off different software on the cluster. This software relies on changing what we call environment variables, because all the internal operation of how a system, a Unix system, search for software packages depends on the content on some of those environment variables. So let's explain a little bit what the environment variable is from the shell perspective, and later in a minute we move into seeing what it is. So let's go back here and share back this. Okay. So now we are in the next session. So we move here from the terminal-based text editors and now move into environment. So let's explain a little bit what an environment variable is. On the shell, that piece of black or white terminal that you see here, the machine, that is, you are actually running a program, a code, a package that is called the shell. There are different variants of the shell or implementation of that. One commonly used is called bash. That's what many people use, or many Linux and Unix distributions use. It's not the only one, and some others use Dash, which is like a variant of that, or Core Shell that was popular, well, relatively popular, like 20-30 years ago, or C Shell, which is also popular for, especially for system administrators. Some people in some areas have that preference for that. So we have a variety of shells. Well, for most part, they work the same. And the nuances appear in loops or in certain little more obscure executions, but for the most part, they run the same. So now, that's why I am focusing in one that is called bash. That's what you see here, calling bash. And here I am declaring a couple of variables. Why? Because the shell itself is an entire programming language. You are running inside a code that is also a programming language. It's called shell. And programming that is doing shell scripting. And that is the topic of the last hour of the last session of this work. Shell scripting. So we have two variables here. Those two variables can be exported and can become like global variables, something that the shell takes for its operation even deeper, let's say, more register those values in a more considering more important. We will see the example. So we have two variables here, and I'm exporting those variables. Another way of doing that is directly creating the variable and put the export in front of it. So you are creating those variables. There is one example here to show the different. Let me see. I'm probably need to go back to demonstrate this. Let me see the difference. Let me see what it is. Oh, it's in file. Okay. Okay, is this. Imagine that we have A equal 4 and B equals 7. And we execute this some message. What I did here was creating a couple of variables, but those variables only exist on this shell. I can do an echo for A, and A contains the value 4. And I do the same for B, and they contain the value 7. But if I execute a script and a code that uses A and B, that script doesn't know what A and B is. But if I export this, so when I do this, export B and or export A, because A already has a value, they are still variables, but now they become environment variables. They exist not only in this shell, but also in the subshells or shells that are created from this execution, from this shell. So now if I execute again this code, it knows what A is, what B is, and is capable of producing the result Z. That is the difference between a variable, shell variable, and environment variable. These are the variables that are important for us to change, to also change which software we want to enable or disable on a cluster, on a system. So let's go back and let me to share again my browser. So I hope it becomes clearer what the difference is between a shell variable and an environment variable. And we would like to, will you have some, and we have been using those for the previous session and yesterday for those who attend the GPU session. We have this, which is another way of storing your username. You have a username, which is the name that appears usually appears on your prompt. You have your username. This is how the machine recognizes you as being a legitimate user of the class. And this is your home folder. There is also the scratch folder, the dollar scratch. Those are variables that are populated just from the beginning when you start using the machine, the terminal. And this is, if you want to customize your prompt, as I do, let's say you see that on my prompt is very colorful. It's like a rainbow. Is because I have customized that. If you want to see how is mine, it's like this. It's a little bit crypted, but it's actually changing the coloring and putting the date, my username, because I am usually in different machines. So I need something that tell me very quickly with some highlighting where I am, on which machine, and where I am on that machine. So and what time I execute something or something, just for quickly monitoring for how long a command was operating or something. So you have the date here. So that is my prompt, and that is managed by another environment variable, PS1. Let me see. My username is this. That's my home folder. My username is this. So you can use echo to show the content of a variable. So echo and the dollar and the name of the variable, and we'll show that. So there are three, let's say, well, let's say 2 or 3 for running purposes. Let's say 2 important, very, very important variables that decide where you can find executables, where you can find codes that you can execute. And this is the dollar path. So it will be searching for all these places in order. When I try to execute a command, and imagine that this is a command, it will try to search for this on every single location, following the order. If that command is something with that name exists in one of those folders, each one of them is a folder. Everything from that is separated by a column. That is a folder. Search there. And after it's searching if that command exists here, then it searches if the command exists here. It will go in order, searching for the command. And find it, will execute that. Otherwise, at the end of the full exploration, it will say, I'm sorry, but that command could not be found. That is an important variable. And the other variable is for execution purposes is this library path. This variable will declare where are the locations for libraries, for code that is functions that are compiled, and other codes can search for them. So this is an important value. When you execute things and you receive messages that something cannot be found, the library is missing, it's usually that something is that you need to add something on this variable, directly or indirectly, when you load the model. We will see that. Let's go back here and better understand how you activate and deactivate software on the class. So environment modules is a software package. It's not the only flavor of it, but this is the original version of it, that allow you to change those environment variables that change the exposition of a certain package to be found when you type it on the terminal. Loading modules or unloading modules is, for most part, all that you have to do to get access to a code. There are a few commands that you need to execute, you can execute to get an idea which commands are available, loading, which modules are available, loading a module, unloading a module, showing what a module does, get some help on what you can expect from that module, or all those things. Is module and a space certain word, and I will do that in a minute. I will skip this for this session. I will just, let me see. Yes, I will explore this with my terminal and show you what we have here. Okay. Okay, module avail. This is the first one. The command module avail, which is the second one in the list. It will show me all the modules available on Thorny Flat right now. Let me see what we can see here. They are organized following roughly a progressive clustering. So here on this level, at this level here, what you have are libraries, compilers, everything that is very low level, not scientific codes per se, but usually libraries or dependencies, things that you need to have for compiling a code or later on for using another code. So you see here in this section languages, in this block here, you see different compilers from different implementation of those. So, well, yeah. Yeah, good comment. Compilers. This NVIDIA, we used this yesterday. This is an NVIDIA compiler, which is very good for working with GPUs. They have very good support for GPUs, very good support for parallel computing in general. It's very informative. So there are a few here. That's fast Fourier transforms that are around here. This is a library for operating with a C code, for example, and doing fast Fourier transform, something that happens a lot in science. This library here, the HDF5, is a library for storing large amount of data with in a standard way, storing large amount of numerical data in a binary form, and being a standard. This is a standard library for storing hierarchically connections or collections of numbers of data, including the metadata. And NetCDF is another one, another library. OpenBLAST is around here, which is a library for linear algebra. So in scientific computing for the last 50 years, so have been people on around 70s for the most part, they create and standardize a library called BLAST, which is a library for basic linear algebra. So matrix multiplication, matrix vector with vector, matrix vector plus a vector plus a vector, something, all those sort of things. All those basic operations that you would like to do with vectors and matrices, all that is BLAST. Now, if you want to do more serious linear algebra or a little bit more advanced linear algebra, like inverting a matrix or decomposing a matrix, doing a triangular decomposition or getting a certain, all the eigenvalues, eigenvectors, all that, is that part of linear algebra is called LAPACK. So many scientific codes rely on those algorithms that have been around for 50 years, and they work very well. What people have been doing are improving the parallelization of those algorithms, and OpenBLAST is one of those implementations that is capable of parallelizing using the multi-cores that we have on computers today for doing this linear algebra operations. So you often would like to use a library like this for your linear algebra needs, basically. And if you want to jump into using multiple machines, there is another implementation for distributed parallel computing. So it's called ScalaPack. And here you have for GPUs, for those who attended yesterday, we have different, the CUDA toolkit, which is the tool that you use if you want to compile the CUDA examples that I presented yesterday for you. You need to use one version of CUDA, and here we have a few. So you see, all that is there. Those are packages, low level. Many users, they don't care much about that. They just use directly software packages for their own research purposes. They work directly. They are users of another package, a scientific package. So they are here on the tier 2 level. And between those, I just put a couple of things that are generic, and that I will be presenting the next session, so on Monday. Conda, which is a way of creating environments that isolate code. Yes, I think we recorded. Yeah, we recorded yesterday the session. I will be available. So Conda, to create environments for isolating software code. This is particularly useful for people in bioinformatics because they rely on a bunch of tiny little software packages, and that they need to work in chain for bioinformatics workflows. So Conda, they have a very nice repository of packages, so people in that area often use Conda, BioConda. We have MATLAB, which is a generic, let's say, software packages for exploring algorithms and doing relatively basic operations in engineering is very popular. And Singularity, which is another way of isolating software. In this time, we are frameworks, PyTorch, TensorFlow, all that, and software packages for molecular dynamics. So we have a variety of software encapsulated in Singularity containers. And now finally, in the next level, we have what most people really care about, which are software packages that they will use directly. So we have a few for engineering here, ANSYS, codes for computational fluid dynamics. So in astronomy, in atomistic, we are talking about everything that when you move particles around, even if not necessarily atoms, but particles. So we have different levels of different software packages for electronic structure, molecular dynamics, and let's call it quantum chemistry to a certain point. Here, and particle, so everything that moves, for example, with the Newton laws, should be in lamps, or it's down. This is a big collection. So GROMACS, lamps for particles, all that. And bioinformatics, we have a few. And again, most people in bioinformatics, they use directly Conda environments. But for a few exceptions, we have some packages outside of that, and we have them here as modules. So again, for engineering, we have more stuff here for optimization, mathematical optimization, which is popular in business, in economics. So we have a few things around here. And so all those scientific package, if you want to load one of them, they will give you the package associated to that particular code. And finally, here we have some generic modules that will themselves load a collection of modules. For example, if you want a variety of languages, so the main languages are Python, Julia, C, C++, Fortran. There is one module here that will load all that, and including Java. So it will load a big collection, and when you are exploring more for developers, it could be handy to have something like this. And after that, we have some extra packages that are created directly by Intel for their own compilers, or Intel compilers. So the compiler itself, the MKL, which is another implementation, an Intel implementation of BLAS and LAPACK, optimized for Intel processors. So MKL is there. And they have their own re-implementation of MPI, the Intel MPI. So all that are the environment modules, and with this, you know that. So now, imagine that you want to use something that is in the atomistic section, which is something atomistic, and we just hit tab, and you know that is the way you load a module. What you are doing here is changing your environment variables, such as the command abinit become present. It should fail. Yeah, it should fail. Okay. So now the command abinit that was not before, now it is present. That particular package relies on a number of some other packages. So this, in this case, it is on the background loading all those packages that are needed such that this main package can be used, or can operate correctly. So you know which packages are present on right now on my system, on my terminal, with this module list. Okay. And if you want to clean your environment, another thing, please, that what this is doing is changing my variable path for this session to add a bunch of other locations such that the abinit is present and the libraries that abinit needs to work are present. If you want to clean that, is with the command module, and you unload all those modules, and you see the list of modules, nothing, and abinit is no longer a command. That is the whole point of using environment modules. You use that a lot. So that's one thing. What I will be doing now is presenting the final topic. We are on time. We're pretty much on time with this. Okay, so I return here to this. So I will be moving to our final episode here, which is the most important thing that you need to learn. So really pay attention to this, because this is what you will be doing if you are starting your graduate student. This is if you are really using the HPC cluster for your research, you will be executing this many times. So you need to do it well. You need to be efficient with this. Otherwise, you will be, as I would often say, you will be working for the computer instead of the computer working for you. So now, imagine that you need, for example, you are working in chemistry and you want to do a simulation with some atoms that are moving, they are colliding, they are doing something, and you need to test that many times with different solvents or under different physical conditions, pressure, temperature, all those. So you will be executing multiple jobs exploring what happens here, what happens there. What the results of those jobs will change your needs for more jobs. Some of them will fail, some of them will produce garbage. So you need to read and learn, and from that learning, you will be adapting, generating, exploring, maybe interesting things emerge, things that were unexpected, which is typically will give rise to a good paper, something that was not expected, and it was found somehow with the search. All that comes from making simulations. You cannot do that efficiently by opening an interactive session and on demand and running the one single execution. It will be very efficient. What do you end up doing is preparing jobs, preparing an entire execution that will happen without your presence when resources on the cluster became available. That is the whole point of submitting jobs. The schematic of this is a little bit like this. You are at home, you are in an office, you are wherever where you are. You connect to the login node here, the login node of the cluster. Or you are using the portal and you open the terminal. Somehow you get access to the login node. Behind that login node, there are a bunch of compute nodes that we see here with tiny blocks. They are graphic representations of compute nodes, an entire computer that eventually can run your job, your execution. Attached to those computers, they share some storage locations, and from those you can write in particular in two, the home and the scratch, and I'm putting the variables there to represent what they are. So all the computers on the cluster are able to see your home folder, are able to see your scratch folder, and you can write there when you need. What you will be doing is, with a small text file, you will be indicating the computer, the system, the software package, the manage, that will orchestrate your execution. Which are your needs in terms, and the needs played in let's say 3 major currencies or elements, which is computational power, that is representing a number of cores that you need, for example, or eventually number of machines that you need if your code can use multiple machines for a single job. So that is computing power. Another element is, along with the computer power, the pure computer, the amount of memory that you need during the execution of the job. It's hard to know, but the experience from previous jobs will tell you how much memory you need. So next time you better target your memory needs on a job, and the amount of time, which is another thing that in principle you don't know for how long will be run, but the experience with previous jobs will better refine your understanding of what you need in terms of time. You play with all those things, and you indicate with certain specific lines that we will learn today, how to declare that to the system, to the resource manager, to SLearn, which is the resource manager that we are using. All that, and it will take your job, and it will put it to run when the resources became available on the cluster. So it will try to decide what is the best way to satisfy the demands of hundreds of users. They are requesting jobs for being executed on this machine, on this cluster. So that is what a batch system does. And the batch system that we have is called SLearn. We used to have another called Torque. The commands have changed, but now we are entirely showing how to use SLearn. So this is something that could be new for those who used the cluster years ago, but not. I'm coming back. So imagine that I have a script like this. So I think I have it here. Well, I will. Why I have this on a script that does nothing really, but this is what's supposed to have the actual execution that you want, calling your scientific code, executing the code, and returning the result. Here, you write a file like this with this content, which is, you can understand it in two parts here. So the first part is this. This, by the way, is called bank, because this is a bank, how we call it. And this is basically indicating that the code that is below this is written under a certain shell programming, shell code. In this case, we're saying, okay, the code below is shell. Well, it's not, it's more generic than that, but that is the purpose of this line. It should be the first line, the very, very first line in the text file should be this. No spaces, no extra lines, is there. Now, the important portion of the code is this, and this you can divide it in two portions. The first portion, which is this, from the point of view of the shell, this is a comment, because in shell scripting, everything that starts with a sharp is a comment. So the shell will ignore this part. But there is a program that you run this in front of, you run this script in front of a program that will read this portion, these few lines, and it will interpret those as your resource, your demands for resource on the cluster, in terms of number of nodes, number of processors that you need, not time, and a few other things. So here I am explaining on this table what is the purpose of each of those lines here. The name, the partition, for example, on which location. We will explain that in a minute. So specifications for resources that you need for this job. And here is what the job should be doing. Eventually calling another code, doing something, and you can even put some extra programming here, executing something. If the result produces this, after that, do this. It produces something else, do something else, or recalculate under the different circumstance or something like that. So you can produce workflows that is typically, for example, in bioinformatics, when you are cleaning something, and after aligning the genome, and after doing something, and after doing some analysis with that. So you change operations, and you can do that here on this section of the code. So let's review a little bit before I go and produce an example. What is those resources mean? So here, the wall time. The wall time is the amount of time that you want the job to run. You need to declare it in advance. If you don't know, you take a rough estimate, a very conservative estimate, and you play with it. Later on, you refine that for other jobs. So here I'm saying I want to run something for 3 minutes. This is hours, minutes, and seconds. A good rule of thumb is, once you know the amount of time that a certain job takes, you put an extra 20% just in case that the processor for some reason got load with some extra operation that decreases the performance of the execution. So you put a conservative couch an extra a gap 20%, 10-20%, just to your job to have some extra time to finish. That's one thing. Another thing is that this will also limit something that we will discuss in a minute, the partition, on which partition you can run. Okay, so in this case, probably let's go and do it, because I have this here to demonstrate this in practice. So what I did for this is that I have, okay, I put it here. So okay, so I originally create here this sleep. Okay, yes. So this code is not doing anything. This is just for demonstration purposes. So I just asking to run for 3 minutes, 30 seconds using one machine and 2 cores. Yeah, here I'm just saying, okay, please print for me on which machine I'm running, what is the date when it was running this, and sleep for 120 seconds, so a couple of minutes before leaving. Why? Because just want to show you how this looks like when you submit the job and all that, and I will be using this under different circumstances. So I have this sleep in place, mimicking that the execution takes more than a few seconds. So it takes some time, so I can monitor some. So let's do that. That will be, this is the file that you write with your text editor. That's why you need to learn at least Nano, because this is the kind of files that you will edit in often on the class. I will be submitting this job, and you will see that we will reiterate that in a minute, how you submit jobs. You submit jobs this way with the command sbatch. That's the way you submit the job. When you submit this job, sbatch will read all those lines that start with batch, all those lines here, all those lines, and it will interpret those lines, the time that you request, all that. You can monitor the job this way. It will show me that the job is running and has been running for 26 seconds and is running on this machine. This is not the head node. This is another machine. It's a compute node that has been assigned to me. The system gives me access and on full control of 2 of those typically 40 cores. I got 2 cores of those 40 for me to execute this. The code will run for like 120 seconds, so we'll finish in a moment. But it's still running. You see that it's running because you see this R here. The job has a name, so you can put names to the job so you know what it does. So something that makes sense to you, and it probably is now. It should be finishing right now. No, sorry, I asked 120 seconds, so 2 entire minutes. Okay, so it will run for 30 seconds. And the job ID, this is the job ID. This is this is something that I got here. So when I submit the job here, I got this number. This is a unique identifier for my job on this cluster. I think that is now done. It's gone. So no longer there. The job has finished. That's how you submit jobs. And now imagine that I do something else. This is what is in the exercise or in the orange box. Imagine that I'm changing this here And instead of 3 minutes, 30 seconds, I am just asking for 30 seconds. So this line of shell will sleep the execution 120 seconds, but the job was meant to run for just 30 seconds. So you will see what happens if I submit this job. Now it's running, and it can only run for 30 seconds. If I exceed the 30 seconds, it will kill the job. It will forcibly kill the process on the remote machine, this one, that just by chance was the same that I was using before. It doesn't need to be the same. I can get one of the 178 machines almost randomly, or at least one, those that are available. They will pick one, and it should be killed. Why is not killing? Do you understand why it's running? It should have been killed.